So let's go ahead and code some confusion matrices. Want to do that? So we will start by copying our last code over, which I think is example 6, into example 7. Oh, 67, not quite what we want. So here I am on example 7, and that's kind of training a number of classifiers. So first of all, looks like my last one didn't save fully, but that's okay. So I want to go 1 verse 1 for the classifier I'm going to use, just because it proved to be faster on our data set, right? I'm not saying it's better or that's the one that you can always use, but it's faster, so it saves us a little bit of time. I'm going to go ahead and hit F5 just to make sure that runs. All right. And so make a prediction for every case, kind of using our k-fold method. So I'm going to say, make a prediction for every case. Y underscore train underscore predict is equal to sk dot model underscore selection dot cross underscore val underscore predict ovo underscore clf x underscore train y underscore train cv is equal to 3. That's going to give me cross validation of 3. And okay, so the last one trained. So now I can go ahead and make a model. And now I want to make a confusion matrix. So we're going to go con co mx is equal to sk.metricx dot confusion underscore matrix y underscore train comma y underscore train underscore predict. So currently running a prediction, and then once that's done, I will build a confusion matrix. And let's go ahead and print confusion matrix. Oh, confusion MX is what I called it. And it's still running my model. So I'm just going to have faith that this is going to work. So let's go ahead and plot our matrix results. So fig is equal to plt dot figure. I'm just going to make it square because I want my confusion matrix to be square. So it's fig size is equal, I need a tuple 4, 4. Okay. Trained my model. And I can go ahead and print my confusion matrix. All right, that looks pretty good. I see it's got bigger numbers on the diagonal. So kind of what I want out of a confusion matrix, right? Good enough for now. Created my figure, and POS is equal to is equal to plt.im show conf underscore mx. Thank you. That was very needed. Okay, so mx CBAR equal to PLT dot color bar POS. I want to make a color bar on the right side. So CBAR dot set underscore label. I need to open up a string for that. And that's going to be number of classified digits. Ooh, my string didn't take. There we go. And then PLT dot Y label. Then it's going to be actual digit. And then I'm just going to copy that down. I don't know why I put an underscore there. Estimated digit. And that's going to be X label. And let's see if that kicks out without errors. Oh yeah, that's not an error. Okay. So this is our confusion matrix for our classifier. Again, it's a stochastic gradient descent classifier trained with threefold cross validation in a 1 versus 1 classifier. And so we made a 1 versus a 2 and a 1 versus a 3 and a 1 versus a 4, and it took the highest number, and that is what it predicted. So it works out quite well for us, right? And again, it's just predicting off of the features, which are the grayscale 256 value for each pixel in our digit class. It's good, but I'm actually not too worried about the diagonal, right? I want to see the noise. So let's go ahead and see how I can see that noise. So we're going to say, look at the noise of the confusion matrix. And that's going to be row underscore sums equal con f underscore mx dot sum of axis equal 1 comma keep IMS equal to true. And now we're going to go norm underscore confusion CONF underscore matrix MX is equal to CONF underscore MX dash row underscore sums. And that's going to take a normalization. Keep DIMS. Sorry, that makes more sense. Keep dimensions. That's going to make a normalized. Look at the noise of the confusion matrix. So maybe I should make that a section. And then this is going to be normalize the predicted values. And now we move to the high values along the diagonal. Now let's remove the high values on the diagonal. I don't know why I just copied all of that. It's not what I want. Con the CONF underscore MX underscore noise is equal to NP dot as array. I'm going to convert it to an array of norm underscore confusion underscore mx d type dot np dot d type equals np dot float 32. We're going to see if that works. And np dot fill underscore diagonal. We're going to fill it with, we're going to fill the diagonal of our confusion matrix. So on f underscore mx underscore noise. We're going to fill that with np.nan, so numbers, not a numbers, and then np.as array. Now that should have filled my confusion matrix noise with NANs on the diagonal. So that looks good. So I've got an NAN here and an NAN here. And now I can go ahead and plot that again. I'm just going to copy my plot code down. But I don't want to, I want to plot confusion underscore matrix underscore noise now. Rerun all of that. There we go. So that is a confusion matrix that I have removed the diagonal on. And that allows me to kind of investigate the misclassifications of my multi-class classifier more efficiently. Any questions on coding up a multi-class confusion matrix? The scale of what? Oh, like if you just wanted to like maybe look at like you don't care about like the high, you could set, okay, yeah, that's actually a good question. I think an IM show, I think there's like a vmin and a vmax. There we go, vmin, vmax. Should we set those and see what happens? Nothing like coding live to see what. So I assume you're talking about like the vertical axis. So I go from like 0 to 0.06. So let's just say I'm just interested in like 0 to 0.02. And I should be, yeah, there we go. So now I can kind of like zoom in on just the small errors here. Does that make sense? So is that what you're asking about? Yeah, it kind of allows you to like saturates everything at the top. So probably a better color bar would be one that like when it gets over yellow, it just goes to white, you know, so you know it's not relevant. But that's just kind of a color scheme that you set up.